Hello everyone, thank you so much for having me today. My name is Sohrab and the title of my presentation, as you see here, is Improvement of Stochastic Instrumentation Data to be Used for Early Warning Systems and Plans for Assiniboine Valley in 2021. Today I would like to start by a brief introduction of the sites that I'm working on. The first one is the famous Ripley Landslide. The Thompson River Valley south of Ashcroft in BC hosts several landslides along a 10-kilometer section of it. Ripley Landslide is moving on a fully developed subhorizontal highly plastic shear zone. Due to the presence of two important railway lines across its toe, this corridor is significant and it has vital economic value. The monitoring has showed an annual cycle of slope deformations, mostly active between September and May, with the annual displacement between 60 and 100 millimeter, and the average horizontal velocity between 0.2 and 0.35 millimeter per day in that time period. As a result, in the landslide classifications, it falls under the category of a slow to very slow. For monitoring purposes, some instruments are required that are flexible, simple to install and operate, easy to maintain, and have the capability of capturing information as much as possible. Figure 2 is a plan view of the landslide that shows the location of instrument installed in the area. I use the data reported by GPS and SAA among all of them. The GPS is a radio navigation, timing, and positioning system which tracks the electromagnetic waves that GPS satellites are continuously sending that pinpoint the antenna position. In the right picture, you see an image of a GPS antenna. Three GPS units, shown with red circles in the figure 2, are here used to report the superficial movement of the mass, and as you can see, they are installed close to railway lines. Another instrument is shape axle array, or SAA. A shape axle array is a chain of rigid segments connected by flexible joints that are designed to resist twist but allow the segments to tilt in any direction. SAA is either vertically inserted in an existing inclined emitter casing or installed into boreholes. Although the application of SAA is not thoroughly the same as GPS, but it still can provide very useful information about the landslide. Another site is the 10-mile landslide located in the Fraser Valley, northeast of the town of Lillooet in southwestern of British Columbia. A section of BC's Highway 99 and a section of CN Railway are within the boundaries of it. The 10-mile landslide is moving with the velocity of up to 10 mm per day on a shear zone parallel to the slide surface with a dip of about 22 degrees. In the past 45 years, the slide has retrogressed approximately 200 meters upslope of the initial tension crack location. This site is where 11 geocubes are successfully performing and providing high temporal observations with a time step of 30 seconds. Figure 6 shows a geocube and the solar panel that provides needed running power installed on this landslide. On the right, the distribution of geocube network is shown on a digital elevation model. The geocube system is a network of monitoring GPS units that works by measuring the relative distance between one unit called as reference point and the others in the network. It is usually said that the geocube is an improved version of GPS with increased accuracy. The current specifications of geocubes allow monitoring an area with a maximum span of 15 km with a spacing of 200 meters to 1000 meters. In this site, 7 of the 11 geocubes placed inside the blue curve as shown in figure 7 are located within the slide, and 2 units, number 44 and number 50, are located outside of the landslide near the border of the tension crack. The unit 69 is located 30 meters uphill from the uppermost tension crack for checking the boundaries of slide. Even though the technology has made monitoring the landslides easier and more favorable from many aspects, it comes with its own specific limitations as well. A very common disadvantage of electronic sensors and instruments is the association of noise with results. The adverse effect of noise on the results might be on different levels, but for the instruments with high temporal resolution, it can severely hit the reliability of an early warning system. The magnitude of velocity is usually used as a threshold for triggering an alarm in those systems. Figure 8 is the horizontal velocity of SAA installed on Ripley Landslide, and the gray points are noisy or unfiltered results. In a very limited window of time, the variation of velocity can be significant, ranging from 0 to 0.8 mm per day, while the filtered results illustrated in brown and black points are confined in a lower limit that obviously increases the quality of measurements. Also, the upper diagram in figure 9 shows the noisy horizontal velocity of one of GPS units that is suffering from noise interference. The lower diagram is revealing that after filtering the results, the real trend might be quite constant in a very limited time window, meaning that the noisy results could have causing a false alarm. Let's look at one more instance too. On the left, you see the velocity diagram gotten from the results of a geocube installed on 10-mile landslide. This diagram is quite fluctuant, and frankly, not only for just an early warning system, but for any purpose, this plot is not useful, because the degree of uncertainty is quite high in determining the velocity at a certain time. On the right, you see a small portion of coordinate diagram that was used to plot the velocity diagram, and clearly, due to the presence of noise, the velocity diagram has become unsuitable. Since the time step between each two consecutive observations is really small, like 30 seconds or 60 seconds, even an insignificant variation in the coordinate leads to a drastic change in the velocity. So it underlines the role of filtering when dealing with the instruments with high temporal resolutions. The red arrows are showing a difference in the coordinates in a time window of about half a day. However, if you look at the big picture, a trend as shown by yellow line is expected to be the real behavior. It means that in the very same time window, the change in the coordinates should be much lower than noisy results are showing, meaning that excluding the noise can decrease the variations as this much. After removing the noise with a filter, a velocity diagram like the one you are seeing right now on the right will be achieved, which is more favorable by all means. So far, it has been crystal clear that noise reduction is essential in processing the data, and the good news is there are some ways to do that. The left diagram in figure 13 shows that the noisy points reported by a geocube installed on 10-mile landslide, and also the processed ones. On the right, you see the velocity diagram gotten from it, shown with blue dots, and the red ones are the filtered results having much less variations. It is again showing that noise reduction can improve the reliability of an early warning system by eliminating the false alarms. However, the question is what filter is appropriate enough for this purpose that reflects the true velocity of a landslide and also does not miss the accelerating moments. So, in short, we expect that the devised filter is able to capture the noise effectively in such a way that the results are as smooth as possible, but at the same time fiercely loyal to the true behavior of the landslide. In this diagram, the blue dots are the horizontal displacements reported by a GPS unit on Ripley landslide, and the red ones are the filtered results by the method that is currently being used and reported to be effective, known as simple moving average. If I zoom in a little bit, it is apparent that the filtered results are not suffering from those fluctuations as before, but a notable time lag exists there for sure. On top of that, the filtered results must be truthful to the inflection points that mark the acceleration moments, since that is the main function of an early warning system. It is seen here that although the current method is serving this purpose somewhat adequately, it could be improved, meaning that a better filter also can be found. To this end, I would like to concisely touch on the methodology I employed to evaluate filters. Different 11 scenarios were generated based on the behavior that are frequently observed in the results of instruments. The first 9 ones are the harmonic trends that might be seen in the slow-moving landslides, while the last 2 are used for assessing the filter when applying it on instantaneous changes. Then, a noise series was generated and added to those scenarios to create the noisy results that we might see as the outputs of the instruments. In these 6 plots, you see instances of a noisy scenario achieved by adding noise series with different standard deviations from very low to very high. These different levels of standard deviations take the instrument dependency into account. In the next step, the noisy databases were filtered by different methods, including simple moving average. By this way, we have the luxury of knowing the real underlying trend that enables us to evaluate the performance of filters. The analyses are not finalized yet, but the early results are really promising. A filter called Gaussian is found to be working in a way that results are smooth enough with no lag, which gives the reliable velocity diagrams and completely synchronized with the original readings, which makes the early warning system to be able to recognize the acceleration points promptly. This filter was chosen to be studied since it can be made to function fast, and preliminary assessments showed that it is more capable of reflecting the true trend of the results than the conventional methods. However, as I mentioned, further investigations on more real-world cases are needed, and additionally, reliability of this filter should be assessed in the next steps to quantify the degree of confidence it is providing in terms of pinpointing the acceleration moment. Alright, I would like to take a few minutes and state our plans in the next year for Assiniboine Valley. The railway track of CN at mile 184.4 on the river subdivision is affected by a landslide. The river subdivision is CN's main line linking eastern and western Canada. In western Manitoba and eastern Saskatchewan, it runs along the Assiniboine and Quapaw River valleys for 37 miles. Figure 21 shows a view of this landslide. Figure 22 is the aerial view of the site taken from Google Earth that is showing the location of survey pins and two boreholes. Into those boreholes showed with blue pins, right now two slope inclinometers are working, from which a sample of these results is showed in figure 23 on the right. They are providing some useful insights about the landslide, like the elevation of shear zone, rate, and direction of movement. One of the intentions in the next year is to replace them with two shape axle arrays. Additionally, 10 geocubes will be spread out in the area in a manner that they span the whole landslide surface, along with one unit outside of its moving boundaries. Eventually, a meteorological station is going to be in place, which its exact location has not been finalized yet, and this decision will be made later mutually with CN. As soon as certain restrictions caused by COVID-19 are lifted, hopefully in the next summer around June or July, these will be in place within a week or so. Installation of these provides an opportunity to gain experience on the performance of them in a completely new environment, which is colder and harsher in comparison to BC. Additionally, we will be able to interpret the results based on the knowledge that has been built up in previous sites. Employing them will be also beneficial to quantitatively detect the impact of any change in boundary conditions such as precipitations on the rate of movement. And finally, for all these, the newly developed filter for processing the instrumentation readings will be used. The long-term objective here would be developing a thorough understanding of the landslide behaviors and controlling parameters. And finally, come up with the appropriate generalizations for the river valley and materials within it for applying them on a LiDAR scale. And these are the references I used for this presentation. Thank you so much for your attention. I will be glad to answer your questions.